Homework pressure? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
So in this question, we have a beam of electrons that pass through a region of perpendicular electric field and magnetic fields. So this is a diagram of how the problem should be visualized. So we have the electric field from plus to minus. Our magnetic field is into the uh, board, and this is the velocity of the electron. And here we have to, in the first part, we have to find the velocity of the electron such that the beam of electrons go undeflected when they pass through this region. So basically we have the net force on the electron, or the net force on each of the electron or all the electrons is 0. So, or I can say that F net is 0. Now let's see what are the forces acting on the electrons here. So first we have the electric force, which is Q times E, and this is along the direction of the electric field, and since this is downward, so we have this force to be down. And also we have the magnetic force, which comes from the magnetic field, and this is given by Q times cross product of V and B. So here we have the velocity and the magnetic field perpendicular, and by right hand rule this will be, I'm sorry, we don't need this, so this will be up or opposite to the electric field. Now since I'm already writing the direction here, we don't need to mark the vector. So now the net field will then be F. Let's take our up to be positive, and it will be Fm minus Fe equals to 0. So yeah, this implies QVV should be equal to Q times V, and this gives, let's write it over here. And this gives the velocity should be E over V. Now you can also use this equation from equation 27.1 in the textbook. So it's already derived over there as well. So yeah, so when we do that, we get our electric field is 1.88 10 to the power 4 velocity, volts over meter, and our magnetic field is 2.6 times 10 to the power minus 5 Tesla. And when we take the ratio, we get the velocity of the electrons to be 7.23 times 10 to the power 6 meter per second. So this is the velocity of the electrons. This should be the velocity of the electrons for them to pass through this region undeflected. Now let's move to the second part of the question. So in the second part, we have the electric field to be turned off, or like we are simply making the electric field 0 here, taking the electric field 0 here, and we have to find the radius of the electron orbit if the electric field is turned off, which is over here. So the only force we have here is the magnetic force, which is QVV. over here, and velocity is given by our answer from part 1, which is 7.23 times 10 to the power 6 meter per second. So if you go through example 20.6, I'll just write it over here. So example 20.6, if you follow that, you'll see that we have a similar situation like this over there as well, and the path of the electron is a circle like. So, and our radius, which we take from this example, is given by mv, mass times velocity over charge of the electron times the magnetic field. So we are using this expression from example 20.6, and this gives, so the mass of the electron is 9.11 times 10 to the power minus 31 kg. Velocity is 7.23 times 10 to the power 6 meter per second. Charge on a single electron is 1.6 times 10 to the power minus 19 coulomb, and our magnetic field is 2.6 times 10 to the power minus 3 Tesla. So we do this calculation and we get the radius to be around 1.58 times 10 to the power minus 2 meter, or 1.58 centimeter. So this is the radius of the orbit of the electron if the electric field is turned off.